Welcome to a series of lectures on mathematical methods and applications. So, we have seen so many things about Laplace transforms. We have seen what Laplace transforms are, what are the important properties of Laplace transform, how can we find out Laplace transforms of important functions, their inverse, etc. In the last lecture, we have seen what unit step function is, how to find out Laplace transform unit step function and some problems based on it. Now, in this lecture we will see what is Dirac delta function and how to find out Laplace transform Dirac delta function and some problems based on it. So, first thing is what is Dirac delta function, or we call it unit impulse function. So, it is defined like this: Dirac delta at t equal to a is nothing but 1 upon epsilon, where a is tending to t tending from a to a plus epsilon and 0 otherwise. And where epsilon tend to 0. So, this is how we defined Dirac delta function. So, if we roughly speaking, if epsilon tend to 0, so t equal to a and this will tends to infinity. So, basically if we speak about the definition of Dirac delta function, so we can say that at t equal to a, that is at one point, it is having infinite value, and at all other values, for all other points, it is 0. Okay. So, whenever we solve such type of problems based on Dirac delta, we always use this definition, that is it is 1 by epsilon when t is varying from a to a plus epsilon, 0 otherwise, and where epsilon tend to 0. So, what does this definition means? This means when a is varying from a to a plus epsilon, where epsilon is tending to 0, then this value is 1 upon epsilon. So, this value is 1. So, a to a plus epsilon, this value is 1, and otherwise this value is 0. So, this is what the graph of Dirac delta function is. This is t, this is Dirac delta function as t equal to t minus a. So, this is how we can define Dirac delta function. So, now the important property of Dirac delta function is that 0 to infinity, the integration of Dirac delta function is always 1. So, that we can easily show 0 to infinity, this integral is equal to. Now, according to definition of Dirac delta function, it is 1 by epsilon when t varying from a to a plus epsilon, so and 0 otherwise. So, this integral has a value only when t varying from a to a plus epsilon, and it is 1 by epsilon dt, and limit epsilon tend to 0, because where epsilon tend to 0. So, this is nothing but limit epsilon tend to 0, 1 by epsilon integration a to a plus epsilon dt, and this is further equal to limit epsilon tend to 0, 1 by epsilon t a to a plus epsilon, and it is equals to limit epsilon tend to 0, 1 by epsilon a plus epsilon minus a, which is nothing but 1. So, that means the total area covered by this function, the Dirac delta function, from 0 to infinity, the total area is always 1. So, we can always define Dirac delta function like this, that this value is 1 by epsilon when t varying from a to a plus epsilon, 0 otherwise, and that where epsilon tend to 0, and the total area covered by the Dirac delta function is always 1. Okay. The next property is we call it filtering property of Dirac delta function. It states that if ft is a continuous and integrable in 0 to infinity, then this integral is always equal to fa. So, this also we can prove easily. Let us try to prove this result. So, what this property is, it is 0 to infinity ft into Dirac delta of t minus a dt is nothing but Fa. So, this property we call it filtering property of Dirac delta function. So, how we will prove it? Now, we will apply a definition of Dirac delta function. So, the left hand side is 0 to infinity Ft into Dirac delta of t at a into dt, which is equals to, now limit epsilon tend to 0 a to a plus epsilon, it is 1 by epsilon Ft into dt. This is by the definition of Dirac delta function, because Dirac delta function attains the value 1 by epsilon when t varying from a to a plus epsilon and epsilon tend to 0. Okay. Now, this is equal to limit this tend to 0 a to a plus epsilon into Ft dt upon epsilon. Okay. Now, when epsilon tend to 0, this is a to a, that is 0, and this is 0. So, this is 0 by 0 form and function is continuous, okay, and integrable. So, we can apply L'Hospital rule to find out the value, because it is 0 by 0 form. So, we can apply L'Hospital rule. So, it is equal to limit epsilon tend to 0 d by d epsilon of a to a plus epsilon Ft dt upon 1. We differentiate respect to epsilon in the numerator as well as in the denominator. Okay. Now, this is equal to limit epsilon tend to 0. Now, when we take d by d epsilon of this function with respect to epsilon, so this is nothing but f of a plus epsilon into 1 minus 0 upon 1. Okay. And when epsilon tend to 0, it is nothing but Fa. So, this is called filtering property of Dirac delta function, that integration 0 to infinity Ft into Dirac delta t minus a dt is nothing but Fa. Okay. So, this is how we can prove this. The next property of Dirac delta is the Laplace transform of Dirac delta is nothing but e की power minus ap. So, Laplace transform of Dirac delta function. So, it is nothing but 0 to infinity e की power minus pt Dirac delta of t minus a into dt by definition of Laplace transforms. Now, by the definition of Dirac delta function, it is equal to limit epsilon tend to 0 a to a plus epsilon into e power minus pt into 1 by epsilon into dt, and which is further equal to limit epsilon tend to 0 a to a plus epsilon e की power minus pt dt upon epsilon. Okay. Now, it is again 0 by 0 form, because when epsilon tend to 0, the numerator is 0 and the denominator is 0. So, 0 by 0 form, so again you will apply L'Hospital rule to simplify this. So, this is nothing but equal to limit epsilon tend to 0, again d by d epsilon of the numerator quantity upon denominator is 1, the derivative of denominator with respect to epsilon is 1, and it is nothing but limit epsilon tend to 0 e power minus p, in place of t we have the upper limit which is a plus epsilon, and when into 1 and minus 0 of course upon 1, and when epsilon tend to 0, it is nothing but e power minus ap. So, that is how we can find out Laplace transform of Dirac delta function, and it is nothing but e power minus ap. And of course, when a is 0, the Laplace transform of delta t is nothing but 1, because when you substitute a equal to 1 in this expression, so we will get Laplace transform of Dirac delta function at t equal to 0 is nothing but 1. Okay. Now, let us solve some problems based on Dirac delta function. Now, whenever we want to find out Laplace transform of some ft into Dirac delta at t equal to a, suppose. So, this will be equal to 0 to infinity e power minus pt ft into Dirac delta t at t equal to a into dt. And when you apply definition of Dirac delta function, it is nothing but limit delta tending to 0 a to a plus epsilon into 1 by epsilon e power minus pt into ft dt, and which is again equal to, okay, epsilon tend to 0, limit epsilon tend to 0 integration a to a plus epsilon e power minus pt ft dt upon epsilon. So, it will become, it will always become 0 by 0 form. So, you will apply a L'Hospital rule to simplify this expression, and then you can get the Laplace transform of ft into Dirac delta or t equal to a. Okay. So, this is how we can find out Laplace transform of ft into Dirac delta function. So, now let us try to find out Laplace transform of these problems. First is Laplace transform of unit step function at t equal to 1 into Dirac delta at t equal to 1. Okay, this. So, this is nothing but 0 to infinity u1t, that is ft. Ft is the entire expression into e power minus pt into dt, which is further equal to, first apply definition of Dirac delta function. Okay. By definition of Dirac delta function is nothing but limit epsilon tend to 0 1 by epsilon a to a plus epsilon u, okay, here a is 1. So, this will be 1 only and this is 1, okay, and u1t into e power minus pt into dt. Now, apply definition of u1t. So, u1t at t equal to t more than 1 by definition of unit step function is 1. So, it is nothing but limit epsilon tend to 0 1 by epsilon 1 to 1 plus epsilon into e power minus pt dt, because u1t is 1 when t greater than 1, otherwise it is 0. So, now it is nothing but limit epsilon tend to 0 1 by epsilon, okay, it is now 0 by 0 form, because you can always write it like this. So, it is 0 by 0 form, okay. So, you have to apply a L'Hospital rule to simplify this. So, it is nothing but limit epsilon tend to 0 d by d epsilon of integral 1 to 1 plus epsilon e power minus pt dt upon 1, and which is nothing but limit epsilon tend to 0 e power minus p, and t is nothing but 1 plus epsilon, and it is nothing but e power minus p. So, that will be the Laplace transform of the first problem. Okay. Now, let us compute Laplace transform of the second problem. It is again on Dirac delta function. So, the second problem is basically e power t involved in this problem. So, it is the Laplace transform of e power t into Dirac delta at a equal to 3, at a equal to 3. So, it is nothing but, so I can write directly, it is limit epsilon tend to 0, instead of a I have 3 here. So, it is 3 to 3 plus epsilon, 3 to 3 plus epsilon, ft is e power minus e power t, and e power minus pt is here also upon epsilon. So, because it is a Laplace transform and I directly apply definition of Dirac delta function. So, it is limit epsilon tend to 0 3 to 3 plus epsilon, okay. It is limit epsilon tend to 0 3 to 3 plus epsilon e power t into e power minus pt dt upon epsilon. So, it is 0 by 0 form. So, you will again apply a L'Hospital rule to simplify this. So, it is or you can first integrate, because it is integrable, it is 1 minus p into 3 plus epsilon upon 1, limit epsilon tend to 0, and it is nothing but e की power 3 1 minus p. Is it so? So, this is the final expression which we can obtain using this by applying L'Hospital rule. Okay. Now, the next problem is Laplace transform of t square into u1t plus t into Dirac delta at t equal to 2. So, this is nothing but Laplace transform of t square into u1t plus Laplace transform of t into Dirac delta at t equal to 2. Now, to compute the first expression, we will use second shifting property of unit step function, which states that Laplace of f t minus a into u t minus a is nothing but e power minus a p into f p, where this f p is nothing but Laplace of f t. Okay. So, we have to break this t square in the powers of t minus 1, because it is f t minus a and a is 1. So, first we find the Laplace of this, then Laplace of this, the addition of this 2 will give the Laplace of the entire expression. So, Laplace of t square into u1t, this can be find out Laplace of, I can write it like this, t minus 1 plus 1 whole square u1t. This is nothing but Laplace of a square plus 2ab plus b square and this is nothing but Laplace of t minus 1 whole square u1t plus 2 times Laplace of t minus 1 u1t plus Laplace of u1t. Now, using that property, it is nothing but e power minus ap, a is 1, so it is minus p into Laplace of ft, so Laplace of t square plus 2 into e power minus p again and Laplace of t plus, and this is nothing but e power minus p into Laplace of 1. So, this is nothing but e power minus p into t square is nothing but 2 upon p cube plus 2 e power minus p into t is nothing but 1 by p square plus e power minus p into 1 by p. So, that is the Laplace of the first expression, Laplace of t square u1t. Now, we will compute Laplace of the second expression. How we will compute Laplace of second expression? It is Laplace of t into Dirac delta t minus 2. Okay. So, this can be written as 0 to infinity t Dirac delta t minus 2 e power minus pt into dt. And applying the definition of Dirac delta function, it is nothing but limit epsilon tend to 0 2 to 2 plus epsilon t e power minus pt dt upon epsilon. So, it is 0 by 0 form. Again we can apply L'Hospital rule to simplify this expression. So, we will obtain this will be equal to limit epsilon tend to 0 2 plus epsilon into e power minus 2 p into 2 plus epsilon into 1 minus 0 upon 1. So, when you take epsilon tend to 0 here, it is nothing but 2 into e power minus 2 p. Okay. So, the sum of these two expressions will give us the Laplace transform of this expression. Okay. Now, the last problem of this slide, Laplace transform of Laplace transform of t square into Dirac delta at t equal to 1. So, this problem also can be solved easily. It is 0 to infinity t square Dirac delta t minus 1 into e की power minus p t dt. And when you apply definition of Dirac delta, it is nothing but limit epsilon tend to 0 1 to 1 plus epsilon t square e की power minus p t dt upon epsilon. Now, it is 0 by 0 form. So, you can directly apply L'Hospital rule to simplify this. So, this is nothing but limit epsilon tend to 0 1 plus epsilon whole square e की power minus p into 1 plus epsilon minus 0 upon 1, and when you take epsilon tend to 0, it is nothing but e की power minus p. So, that will be Laplace transform of t square into Dirac delta at t equal to 1. Okay. So, that is how we can solve problems based on Dirac delta function. I mean Laplace to find out the function with Dirac delta function. Okay. Now, let us evaluate the following integrals 0 to infinity, which are having the involvement of Dirac delta. So, we can directly use filtering property of Dirac delta function. What is filtering property? That we have already proved. So, this is a filtering property of the Dirac delta function, that is 0 to infinity f t into Dirac delta of t minus a dt is nothing but f a. Okay. So, suppose you want to solve first problem. The first problem is 0 to infinity sin square t Dirac delta at pi by 4. So, if you compare this with this expression, so f t is nothing but sin square t and a is nothing but pi by 4. So, directly using this filtering property, this expression will be nothing but sin square pi by 4. Now, sin pi by 4 is 1 by under root 2, it is whole square, which is nothing but 1 by 2. So, directly using filtering property, we can find out the value of this problem. Now, similarly, if we take the second problem is nothing but it is 0 to infinity t square cos 2t into Dirac delta at t equal to pi by 2. Again, if we compare this with this expression, so f t is nothing but t square cos 2t and a is pi by 2. So, by using this property, this expression will have the value equal to t square cos 2t at t equal to pi by 2. So, this is nothing but pi by 2 whole square cos pi, and cos pi is minus 1. So, it is minus pi square by 4. It is minus pi square by 4. Now, let us see the third problem of this slide, that is 0 to infinity. It is 0 to infinity f t into Dirac delta at t pi by 2 dt, and f t is defined like this. F t is given to us, it is 0 when t lying between 0 and pi by 2, and it is sin t when t is greater than or equal to pi by 2. So, basically what this function is, it is 0 into u 0 t minus u pi by 2 t plus sin t into u pi by 2 t. So, I express this function in terms of unit step function. Okay. So, it is nothing but sin t into u at pi by 2 into t. So, now this is equal to by filtering property, this will be nothing but the value of f at t equal to a, and here a is pi by 2. So, the value of f at pi by 2. So, value of f, that is sin t into u pi by 2 into t at t equal to pi by 2. Now, at t equal to pi by 2, this is 1, it is a unit step function, the value will be 1. So, it is nothing but sin pi by 2 into 1, which is nothing but 1. So, hence we can find out the value of this expression. So, we have seen that what is that delta function, how we can solve some problems based on the based on this, how we can solve these type of integral using filtering property or delta function. So, in the next lecture we will see that what are the various applications of Laplace transforms. So, thank you.